Welcome you in the lecture series of random processes detection and estimation. It is the ninth lecture of this series. In this lecture, we will discuss about the objective of the signal detection and signal parameter estimation in discrete time domain. And the outline of this lecture are: what detection and estimation, application of detection and estimation theory, types of detection, mathematical model of detection problems, complexity levels of detection problems. And after this we will discuss about the type of estimation approaches, mathematical model of estimation problem, complexity levels of estimation problems. And in the objective of this lecture, you will able to explain why the need for detection and estimation in signal processing. How can you mathematically formulate the detection and estimation problems? And what is the difference between deterministic and random signal detection and estimation? Now let us start with the what is detection. In detection theory, we have to make a decision on the basis of hypothesis testing. We have to decide whether the signal is present or the signal is absent. And what is the estimation? In estimation, we assume that the receiver has made a decision in favor of the signal is present at the receiver. But some parameters associated with the signal may not be known. So the goal is to estimate those parameters based on the finite number of samples of the signal. So the detection and estimation theory is the branch of signal processing where the process of detection making and the extraction of the relevant information from the noisy signal is done. Many signal processing devices are made to decide that when an event occurs and then extract more information about the event. So let us summarize some application that involves the use of detection and estimation theory. First is the radar system, where the occurrence of the aircraft or missile is to be detected, or the delay of the received pulse echo is to be estimated, which in turn determine the location of the target or the range of the target or the aircraft in presence of the noise. Here to decide the range are: we transmit an electromagnetic pulse that is reflected by the aircraft and echo is received by an antenna. Let tau naught second later we receive the echo. Then the range R can be calculated by tau naught is equal to 2R by C, where R is the range and C is the speed of electromagnetic wave propagation. And another example is the image processing. In this, we detect and estimate the position and orientation of an object from a camera image in presence of noise. It is necessary when using a robot to pick up an object. And another application is the biomedical processing, where we detect and estimate the heart rate of the fetus using the sonography during the pregnancy in presence of sensor and environmental noise. And another application is in the communication system, where we detect the transmitted signal at the receiver side and carrier frequency of the signal is estimated so that the signal can be demodulated to the baseband signal in presence of system and the channel noise. And another application is the control system, where we detect and estimate the position of the boat so that the correct navigation action can be taken in presence of the sensor and environmental noise. For example, LORAN, long range navigation. Another application is the seismology, where the presence of the underground oil is to be detected and the distance of the oil deposit is estimated in presence of surrounding noise. And another application is the sonar system, where the presence of the submarine is to be detected and the location is to be estimated in presence of the noise and some attenuations. And another application is the speech processing, where the presence of different words is to be detected in context to speech recognition application, and the parameter of speech production model have to be estimated in context to speech coding application in presence of environmental noise. And apart from these, there are many more applications, and the majority of applications require detection one or more events of interest and or the estimation of an unknown parameter from the collection of the observed data in presence of the additive noise, signal distortion, sensor inaccuracy, model inaccuracy, and multiple interfering signals. So now we will discuss about types of detection. Detection of known signal or deterministic signal in noise. It is known as parameter detection, where the PDF of data is known, and the parameter detection approach is to the hypothesis testing. And another type of detection is the detection of random signal in noise. The detection of signal when the signals are modeled as random process with known covariance structure. So here the signal which is to be detected, there are some parameters which are unknown and they are modeled as a random in nature. So this type of detection is known as the detection of a random signal in noise. And the detection of non-parametric signal in noise. The signal to be detected in this case is having a known PDF, or we know the PDF in some approximation form. Now we will discuss the mathematical model for the detection problems. First we will discuss what is the decision theory or hypothesis testing. In simple decision or detection problem, we have to decide whether a signal is present embedded with noise, or only the noise is present, means whether the signal is present or absent. For example, consider the detection of the aircraft. This problem can be termed as the binary estimation or binary hypothesis testing problem, and that is the estimation among two hypotheses, chosen the best of two hypotheses, and the structure of hypothesis testing is formulated with the null hypothesis H0, and the rejection of H0 leads to acceptance of the alternative hypothesis H1. The null hypothesis is correspond to no change from usual, that is aircraft is not present or aircraft is absent, and the alternate hypothesis H1 shows the change, that is aircraft is present. And in the decision theory, the objective is to decide which hypothesis one of these two hypotheses is true based on the observed data. A hypothesis testing is this is the simple hypothesis testing if all parameters are satisfied exactly. So in the it can be a composite also. So in the simple hypothesis testing, just like if the hypothesis H1 corresponds to theta is equal to theta naught and H1 corresponds to theta is equal to theta 1. So it is a simple type of hypothesis testing, and when H0 corresponds to theta is equal to theta naught, then this is simple hypothesis, and when H1 corresponds to theta is equal to not equal to theta naught, then it is the composite hypothesis testing. This type of hypothesis testing is known as binary hypothesis testing, that is encountered in some communication. When we decide among more than two hypotheses, then it is referred to as multiple hypothesis testing problem. For example, in speech recognition, our goal is to determine which of the digit among 10 possible ones is spoken. Hypothesis testing is a decision process where we decide the observation space into two regions R1 and R0. Let x is equal to x1 to xn is the observed vector, and if x naught, if x belongs to x naught, then if x belongs to x naught, then we decide h naught, and if x belongs to h1, we decide h1. The region r naught is known as the acceptance region. The region r1 is known as the rejection or the critical region, since the null hypothesis is rejected. Each time each time decision is made based on some criteria. For the binary hypothesis testing problem, 4 possible cases may occur here, and these are: first case, when h naught true and we accept h naught, h naught true but we accept h1, reject h naught, and h1 true, we accept h1, and fourth case is h1 true but we reject h1 and accept h naught. The first and third are corresponds to correct decision. The second and fourth correspond to error. The second case, h naught true, reject h naught, accept h1. It is the type first error or false alarm. When h naught is true and you accept h1, this is false alarm because the target was not present, but alarm or we have decided in favor of the in presence of the target, means there is false alarm in that indicate the presence of the signal. And the probability of false alarm is given by the P1 or PF. This is type first error, and this is the probability of we have decided h1 when h naught is true, means the observed data x belongs to r1, the critical region, but where the h naught is true, and this shaded region is known as the probability of false alarm. P1 is denoted as alpha and is known as the level of significance or the size of the test. And type second error means reject h1, accept h naught when h1 is true. This is corresponds to miss the target, means the target is present but you have taken the decision in favor of h naught and h1 was true. So this is the corresponds to the miss the target, and this type of the probability of this second type of error is p second, or probability of miss target will be equal to probability of decision making in favor of h naught when h1 was true, and the probability the observed data belongs to r naught when h1 is true, and this shaded region shows the probability of miss the target. Type second error is denoted as beta, known as the power of the test, and this region is known as the probability of correct decision in favor of h naught, hypothesis h naught, and this region shows the probability of correct decision in favor of h1. And so the probability of correct decision means the probability of observed data belongs to r naught when h naught is true, and the probability of observed data x belongs to r1 when h1 is true. This is the probability of correct decision. The only way to reduce simultaneously both type of error is to increase the sample size. The size of the critical region and the probability of type first error can always be reduced by adjusting the critical values. The cost of failing to detect the target cannot be easily determined. In general, we set the value of probability of false alarm which is acceptable and seek a decision test that maximize the detection probability or equivalently minimize the probability of miss the target. Consider the example. Detection of a DC level of the amplitude A is equal to 1 in presence of white Gaussian noise omega n with mean 0 and variance sigma square. Let the random samples x having the sample value x0, x1 to xn minus 1 or n samples to make the decision. Assume only one sample now, x0. Now formulate this problem. So this is the DC signal generator, and it generates the A is equal to 1 and A is equal to 0. A is equal to 1. So in presence of noise, when the signal is present, DC level is present, there is a noise and we have received this X. And when the signal is not present, means A is equal to 0, we receive in presence of noise this value of X. So we can map this PDF in two hypothesis PDF. So these are the PDFs shown of the two hypotheses H1 and H0. So when the signal is present or DC level is present, A is equal to 1 present in the signal, this X corresponds to H1, means the signal is present. This is correspond to H1. And when the signal is not present, this means there is hypothesis H0. So this X belongs to this hypothesis. So this observed X belongs to this hypothesis H0 when the signal is not present. So here you can see hypothesis H0 belongs to H0 is equal to omega naught, and H1 hypothesis corresponds to X0 is equal to 1 plus omega naught. In this case, DC level is present in the noise. So we have to decide. So this is only noise and this is noise plus signal. So the PDF under each hypothesis, you can say the PDF, the probability of observed sample X0 when H0 is true, it will be 1 by under root 2 pi sigma e to the power minus x square naught upon 2 sigma square. And the PDF under H1, it will be 1 upon under root 2 pi sigma e to the power minus x naught minus 1 whole square. Here 1 is because the mean value is 1, or you can say the signal is present in the noise. DC level is A is equal to 1. So this is the mean value of A. And here alternatively, these two equations can be represented as the probability of observed sample X0 when A is given. So it will be 1 upon under root 2 pi sigma e to the power minus x naught minus A whole square upon 2 sigma square. And so we can say here the probability of observed sample X0 when H0 true and probability of X0 when H1 true. In the case of when H0 true, the amplitude A is equal to 0, means DC level is not present, only the noise is present, and A is equal to 1 means the noise is present, the signal is present in the noise. In on-off keying communication system, we transmit to 0 when no pulse and transmit to 1 when the pulse having amplitude A. So now the PDF Px0, H0 and Px1, H1 is the conditional PDF. So now we can represent these PDF of the corresponds to H0 and H1. The probability of X0 given H0 1 upon under root 2 pi sigma e to the power minus x naught whole square upon 2 sigma square, and Px0 given H1 1 upon under root 2 pi sigma e to the power minus x naught minus 1 upon 2 sigma square. Now we will discuss the complexity levels of detection problems. The detection problems consider both signal and noise characteristics are completely known. If the characteristic of the signal and the noise are unknown or not known completely, then the detection problem can be complex. There are three levels of complexity for the detection problems. The first level, when the signal in the noise to be detected is known, means the signal is deterministic. For example, synchronous digital communication, pattern recognition. And the second level, where the signal in the noise to be detected having unknown parameters, is digital communication system without phase reference, and digital communication over slowly fading channels. And level third means when the signals in the noise to be detected is random in nature. For example, digital communication over scattered link, passive sonar, radio astronomy detection of noise sources. Now we will discuss estimation problems. In estimation, we assume that the receiver has made a decision in favor of true hypothesis, but some parameters associated with the signal may not be known. Now the goal is to estimate those parameters based on the finite number of samples of the signals. Now, types of estimation approach. Based on the assumption made about the unknown parameters, the estimation methods can be divided into two broad groups. First is classical parameter estimation. In the classical parameter estimation, you have given a set of observation and given an assumed probabilistic model for the unknown parameters. Means we have deterministic unknown parameter and you have to find best estimation. For example, a DC signal in white noise, image recognition parameters, channel model. And another is Bayesian estimation. In Bayesian estimation, the unknown parameter is random in nature and we have to estimate unknown parameters. In these both categories, a number of optimum and suboptimum estimation approaches exist, which are necessary due to the lack of complete knowledge about the mathematical model for estimating the unknown quantity. So the parameter to be estimated may be random or non-random, and the estimation of the random parameter is known as Bayesian estimation, that is estimation with a prior, while the estimation of non-random parameters is referred to as maximum likelihood estimation. Now we will discuss the mathematical model of estimation problem. The model used in estimation problem involves four components. First, the source, whose output depends on the parameter theta. The parameter is either random or non-random, means deterministic, unknown quantity. Second is the probabilistic mapping of the parameter on the observation x. This probabilistic mapping is the joint probability density function px theta. And third is the observation space, which is multidimensional, belongs to either the continuous or discrete domain. And fourth is the estimation rule gx, that is the mapping of the observation space into the estimate of the unknown parameter theta. Let x1, x2, xn be an independent, identically distributed samples of a random variable x with some density function px theta depending on an unknown parameter theta, and let x1, x2 to xn are the corresponding values of the random sample x1 to xn, and g x1 to xn is the function of the sample used to estimate the parameter theta. Then the function phi is equal to the function of the random samples x1, x2, xn, means phi is equal to g x1 to xn is the estimator of theta, and the value of this estimator is known as the estimate value of this theta. So the estimated value of theta is g x1, x2, xn. Here these are the random samples and these are the value of the random samples. So this is the estimated value of the parameter theta. The estimate It is not necessary that an estimate of a parameter is one single value. Instead, the estimate could be the range of the values. Means this theta may have the value or may have the range of values or may have the single value. So estimate which specify the single value is termed as the point estimate, and the estimate which specify the range of the values are known as interval estimates. And the complexity level of estimation problems, there are three levels of complexity. Level first, when the signal in the noise to be estimated is known, means deterministic unknown parameter is there to be estimated here. And for example, pulse amplitude modulation, pulse frequency modulation, pulse position modulation communication system with phase synchronization. And second level, when the signal in the noise to be estimated having unknown parameter, for example range, velocity, or the angle measurement of radar or sonar. Another example is discrete time continuous time communication system with unknown amplitude or phase. And level third, when the signal in the noise to be estimated is random in nature, for example power spectrum parameter estimation, velocity measurement in the radio astronomy, and ground mapping radar. In this lecture, we have discussed about the objective of signal detection and parameter estimation, why the need for detection and estimation, formulation of signal detection and signal parameter estimation, difference between detection and estimation. This was the lecture 9th of the lecture series of random processes, detection and estimation. In the coming lectures, first we will discuss about the detection theory, then we will discuss estimation theory. Till then, thanks for listening this lecture. Thank you.